I'm very happy to be here and to be in this great place, the Open University. I've been here several times before, both as in the audience of this day, in earlier years and in other occasions, and this is really an institution that I think we can all be proud of. And regarding my lecture, I should also apologize to people who heard me talk about similar things. To those of you who already heard me, to those of you whose parents already heard me about similar things. Now let me see. This should work like this. Ah, maybe this relates to the. Okay, I will it. So what do we do now? Here, space. Okay, here's the plan of the talk. And we start with Boolean functions. And I will try to describe three important concepts regarding Boolean functions. The first is the influence. This is something I was influenced from Nati, who is here. The second is the noise sensitivity. And the third is the Fourier expansion. This is a mathematical tool to study Boolean functions, but we can regard this as a basic concept about them. Then I would like to mention three basic theorems. I don't know. Okay. The first is a theorem from 1988 by Gil Kalai and Lineal. The second is a result from 1999 from of Itai Binyamini, me and Oded Shram. And the third is a result from 2005 by Mosel, O'Donnell, and Oleskevich. I also will mention a result by Shepard from 1999. And then I want to go ahead to describe two conjectures. And the first conjecture that I would like to discuss a bit is the relation between noise sensitivity and the bounded depths polynomial size threshold circuits. And although this conjecture is also from the paper with Itai and Oded, I think it's not so much well known, so I'll try to discuss it. And I have also a plan, although I think this is the place I will arrive to, but I have also a post-mortem plan. So if I will have time, or let's say I will not have time, but had I had time, I would also mention another conjecture, which is the influence entropy conjecture. And just to tell you that things are still happening in this area, I would have liked to mention two generalizations. One is a work with Elchanan Mosel, which deals with sharp threshold for larger alphabet, and another is a work with Muli Safra and Moshe Tenenholz, which studies specifically function, sort of an extension of Boolean function, but this time it's function from -1,1 to the power nk to -1,1 to the power k, which has several interpretations. And oops. Okay, and since this will come at the end, I want to mention already this conjecture, so some of the terms will be clarified later, but the conjecture says that if you have a bounded depth polynomial side threshold circuit, so this is some computational device which is more general than Boolean circuit, because the gates are not necessarily Boolean operators, but also allow a threshold. They are threshold gates, so they allow majority function or weighted majority function. And the conjecture is that if you have a monotone function described by such gadgets, then this monotone function will be fairly stable to noise, which means that the value of the function will not change much if you apply a small noise, and here by small it should be 1 over poly the poly of the size to the power of some constant times the depth, but let's just say small. So the value of the function will not change much if you apply small noise. And this conjecture will allow, I think this conjecture is realistic if we restrict ourselves to monotone bounded depth, to monotone circuits. It's a little bit science fiction if we talk about general threshold circuits, and it will be natural and it will have nice implications. So this is a conjecture I would like to mention toward the end of the talk, but for the experts who knows everything that I'll say in the beginning, they can go ahead and think about it. Here is the conjecture. Let f be a monotone Boolean function described by a monotone threshold circuit of size m and depth d. Then f is stable to 1 over t noise, where t is log of the size to the power 100 of the depth. Okay, so we will come back to this conjecture. But okay, here's part 1, and I want to talk about Boolean function. 3 basic notions. So this is what Boolean functions are. Let me just. So Boolean functions are functions. This is an opportunity to point at the screen. Usually I just point at the screen in the computer and I say, here, okay. And somehow the students don't react so well to that. But after Shafi talks, when she explained the benefits of this screen, I really want to make use of it. So we consider Boolean function. So we have n variables, which are Boolean variables. They have values -1 or 1, and we have the domain. And the function also gets one of the 2 variables, -1 and 1. And we will regard -1, 1 to the n, the space of all strings of length n, as a probability space with the uniform probability distribution. I should say everything I talk about can be extended to other product distributions. And this extension is of some interest and importance in this theory, but we will not do it at all in this lecture. And also that it's very interesting to study this space for other probability distributions, which are not product distributions, but there, all the hell breaks loose. This is the right, and really things are very basic things about the uniform distribution. You have to reinvent them from scratch. And Boolean functions are quite important gadgets, of course, in computer science, and also in mathematics, in combinatorics, which is where I came from, and in probability theory, and in other areas, in reliability theory, and in social choice theory, and in various other cases. This works. Amazing. Now, okay. So the first concept I would like to mention is influence. So we consider a Boolean function. Again, this is a function from -1, 1 to the n, from strings of length n of n variables to -1, 1. And the influence of the case variable, xk on f, denoted by ik of f, is the probability that flipping the value of the case variable will flip the value of f. So I will give so is this definition clear? I'll give some examples, which I hope it will stay clear after the example. The total influence, which is denoted by I of f, sometimes it's also called the average sensitivity, is the sum of all individual influences. Examples. So here is a function, and the name of this function comes from one of the places Boolean functions are used, which is in voting rules. So voting rules are ways you have 2 candidates, and there is an election, and you want to aggregate the votes, the ballots or the votes of the individual to the outcome of the election, and a way to do it is called the voting rule. And this is a very simple and useful voting rule, which is called dictatorship. And here the function is fx1 up to xn is equal to x1, And in this case, the influence of every variable is 0, except for the dictator, and for k equal 1, the influence of this variable is 1. So if we flip the value of the 7th variable, this will not affect the outcome of the function. So this dictatorship. There is another class of functions which are quite used in applications in theoretical computer science, which are called juntas, which are like dictatorship, except the function depends on a bounded number of variables. And there are interesting things to say about influence of juntas, but let me move to another function, which I think some of us prefer more in the case of election, which is the majority function. So f of x1 up to xn is 1, if and only if the sum of the variables is greater than 0. And in this case, the influence of the case variable behaves like 1 over square root of n for every k. Of course, all the influences are the same because this function is completely symmetric. And the fact that this behaves like 1 over square root of n, I think it's an important mathematical fact that if you have a drunk person who moves with 1/2 probability to the right and 1/2 probability to the left, and you ask what is the probability that after an even number of moves he will end up at the same place he started, then this is roughly 1 over square root of n. So this is a well-known fact in probability theory, not hard to prove, and this is essentially the same thing. So here the influence behaves like 1 over square root of n. Well, I see I don't have parity, so this is a good example. What is the? Suppose that the function is the parity of all the variables. What is the influence? 1 for every. If the function is the parity function, then the influence of every variable is 1. Okay, here's another example. In this example, you have the variables correspond to these hexagons, and according to being 1 or minus 1, we color the hexagon white or gray, and the value of the function is 1 if there is a pass from top to bottom, which is all gray, and it is minus 1 if there is a white pass from left to right, which is all white. Okay, so these two things. I don't know what happened in this picture. There is black top to bottom. Right. Yeah. Go like this and like this. You see here, I can use this invention really optimally. And let's see. And for the crossing event for Percolation, again, this is just the definition. Here, the influence of every variable, except a few variables on the boundary, behaves like n to the minus 3 over 8. And this fact is already an extremely difficult fact to prove. So it really uses all the high machinery about this model, the Percolation model. I think the Percolation model is a model, if you are not familiar with this model, it's something worth putting in some drawer in your mind, because it's a useful model, and in this case, much advance happened in the last years, and all these wonderful theorems enable us to say, this was conjectured for a long time, to actually prove this statement. More examples. So here is the example of recursive majority of 3s. Here you have something like majority, except you divide the society to 3 parts. You divide the society to 3. Say you divide your country to 3 states, and then you divide each state to 3 counties, and each county to 3 cities, and each city to 3 neighborhoods, and each neighborhood to 3 streets, and each street to 3 buildings, and each building to 3 houses, and each house to 3 apartments, and each apartment to 3 people. And then you take majority recursively upwards. Okay, so I hope this explains what is this function. And here, ik of f behaves like n to the power minus log of 3 to the base 2. I couldn't do this subscript of superscript in PowerPoint for every k, not by a few. No few. The few is a copy from, yeah, without any exception. And then the last example is the Benor linear tribe example. And this is really a remarkable example that Nati and Michael Benor found in '85. Divide the variables to tribes of size log n minus log log n plus log log of 2. Yeah, this is what you should do. And f. What? Yeah.
Well, I mean, is to get example with more logs.
And f is 1 if and only for some tribe all variables equal to 1. So this is the voting rule. You divide your society. Let the society be divided to parts of log n minus log log n plus log log 2 precisely, and then the referendum, the answer to the referendum is yes if there is a tribe that all the members of this tribe say yes. So this is an example by Benor and lineal. Actually, the recursive majority of 3 is also an example by Benor of lineal from the same paper. You can wonder why I mention it here and not here. And the only thing I can say is I can tell you the following joke, which is slightly resembling that a guy came to visit his friend who had a farm, and he saw there are 2 cows, a black cow and a white cow. And then the farmer said, "Look at this black cow. It's a wonderful cow. It gives me 100 gallons of milk every day." So the friend asked him, "That's very impressive. And what about the white cow?" He said, "Also." And I said, "You know, this black cow, it doesn't need any, she doesn't need any food. I don't need to pay any amount of food. She really, that's very impressive. What about the white cow?" I said, "Also." And I said, "You know, this black cow, she was not ill for a single day during her life." Again, the friend is very impressed. He said, what about the white cow?" And the farmer said, "Also." And then the friend is really puzzled. And he asked him, "But why you tell me all this wonderful thing about the black cow? I mean, the white cow seems as wonderful as the black cow." The farmer said, "This is very simple. The black cow is mine." And he said, "But what about the white cow?" And he said, "Also." That's it. So in the case of the tribe example, the influence of every variable, and this is not a difficult exercise, behave like a constant log n over n for some constant k. So this was our first notion, the influence of variables on a Boolean function. Now come our next notion, which is noise sensitivity. So again, we consider, there are surprises, but again, we consider Boolean function, and here we consider the following situation. It's not so far away from influence, but this time we look at the variables x1 up to xn, and then we look at a new set of variables y1 up to yn, and in this case, xi is equal to yi with probability 1 minus t, and xi is equal to minus yi with probability t. So you can think about it as we have an election, the voters voted, and then when we count the votes, there is a mistake with probability, with small probability t. So this probability is not so small as 1 over n, in which case this will be more or less the influence, but it's some constant probability. And then we say, and then we consider the correlation. The correlation between the outcome of the election for the actual votes that the people casted and the outcome of the election after the votes were counted. And noise sensitivity, a sequence of Boolean function is called noise sensitive if this correlation tends to 0. And we will also describe the sort of the opposite notion, which is noise stability. And for simplicity, for this lecture, we'll fix a small number, which will be 0.0001. And then we say that a Boolean function is noise stable to noise level t if the probability that f of x1 up to xn is different than f of y1 up to yn is smaller than s. So if the probability that, flipping at random a t fraction of the variable change the outcome of the function, or if you want to think about it as the election rule, change the outcome of the election. So actually, so this notion, we, yes?
Can you go back to the previous slide?
Sure. You can go back from here or from here?
No, actually for the...
This one?
No, when you define the node sensitivity, is it for every x1 to xn or?
No, when we talk about the correlation, this is a good question. When we talk about the correlation, we take x1 up to xn at random and y1 up to yn at random. So x1 up to xn are uniformly distributed, and y1 up to yn are distributed according to this rule. So we look at it's a probabilistic notion. So these are the notion of noise stability and noise sensitivity. Now the third notion, it's a technical notion, and this notion, there was a recent technical breakthrough, although incomplete breakthrough, which is, this is a description of a Boolean function by the Fourier description of a Boolean function. And if we have a Boolean function, the Fourier expansion is simply an expression by monomials. So if we have the function f of x, we write f of x is equal to f hat of s w of s, where w of s is the monomial, the product of x little s, s belong to s.
There is a sum missing.
There is a sum, you are right. There is a sum missing here, so, well, this I cannot. Here should be a sum. I can add the sum, but there are some other troubles. Okay, so I should say here there is the sum. I didn't know how to, you see here, before, a few days ago, the only thing I knew how to do is to have this hat here, next to the F. But then I met Oded Regev, who was already mentioned earlier, and he explained to me how to do the hat above the F. You have to put some numlock and then alt 770. I tried it on my computer, but instead of having a hat on the F, it put a little smiley beside the F. But then when I did it on in the office computer, which has a more recent, it really makes a very nice hat over the F, like here. But then this computer, which is probably in between this really glorious hat, somehow shrank and moved to the... So this is F hat, and I hope you'll be able to distinguish. In any case, the expansion of Boolean function and even non-Boolean function in terms of monomials are precisely what is referred to as the Fourier expansion or Fourier-Walsh expansion of a function. And the coefficient, and one of the interesting facts is that studying Boolean function in terms of Fourier expansion turned out to be a fairly useful tool. And one of the first things, so these monomials form an autonomal system of function, and this implies that the sum of the square of the Fourier coefficient is precisely the average or the mean square of the values of the function, which is, we know, 1, and this is so-called Parseval formula. So the sum of the square of this Fourier coefficient is always 1. So when we have a Boolean function and we look at this Fourier coefficient, we suddenly see a probability distribution on subsets, which is described by the square of the Fourier coefficient. So every Boolean function that gives you some probability distribution on subsets of 1 up to n, and this probability distribution have a lot of connection with combinatorial and even computational properties and probabilistic of the Boolean function. Okay, now that I introduced 3 notions, let me mention a few connections. So I already mentioned that the sum of the squares, and again, all these hats, you should have seen the hats in their glorious time, but they all shrank. But I hope you can still see the intention. The sum of the square of the Fourier coefficient is 1. The influence of the case variable can be described by the sum of the square of the coefficient which correspond to sets which contain the variable k. So if we look just the sum of the square of the coefficients which correspond to sets which contain k, this is precisely the influence of the case variable. And now if we sum over all variables, we get this very lovely formula which says that the influence of the function, the total influence of the function, is precisely the sum of the squares of the Fourier coefficient of s times the size of s. So it's sort of it's the expected size of the Fourier of the s. Now we can think about sets, large sets, as high frequencies. Since we think about this as Fourier expansion, this is not the Fourier expansion, the real Fourier expansion that Peter mentioned, but it's some sort of Fourier expansion, and we can think about small sets as low frequencies and large sets as high frequencies, and you see that the influence is the expected frequency in this way of thinking about it. Now what about noise sensitivity? This was our second description. So it turns out that the spectral distribution f is, this I already said, the spectral distribution is the probability distribution which corresponds to the square of the Fourier coefficient. And now a sequence of function is noise sensitive if for every k the overall spectral probability for non-empty sets of size at most k tend to 0 as n tend to infinity. So you look at the function, you look at the Fourier coefficients, and if you have a sequence of functions so that the Fourier coefficient leak to high frequencies, then this is equivalent noise sensitivity. If most of the Fourier coefficients belong to small frequencies, to small sets, then this is equivalent to noise stability. And you can have intermediate situations. But this is the Fourier description of noise stability and noise sensitivity, and you see that it's not far from the notion of influence. Influence talks about the expectation of the size of S, and noise stability talks about where it is supported, where the Fourier coefficient or where the energy of the function is supported. So these are the connections. Okay, so these were 3 notions about Boolean function, and now I want to talk about 3 important theorems. So the first theorem, I don't know, I mean, it's not so nice to mention my own theorem to say they are important. I mean, but it happened so many years ago, so I see no relation between me now and So the first theorem I think this theorem is sort of a nice story how ideas go back from theoretical computer science to mathematics, back to theoretical computer science in other areas, to combinatorics, probably. So it was very nice. I think the start of this theorem, start of this study by Miki and Nati was about collective coin flipping, which is something in between distributed computing and something cryptography, or I'm missing something, but something like that, yeah, something. So it's really it's sort of a fascinating area, and it's very nice to explain to mathematicians. I talk about collective coin flipping, and they say, look, but you can. Why don't you take just a bit at random among all these n bits of the processor? Why don't you take the bit at random? I'm not, I didn't born to this problem, so I have to think for a while there. Yeah. How do you find the random bits to choose a variable at random? So there are really some subtle things there. In any case, this is a very nice area, collective coin flipping, but I will not talk about it. The theorem is let f be a Boolean function, and suppose that the probability that f is 1 is t, then there is a variable k such that the influence of this variable is bigger than a constant times t times 1 minus t times log n over n. And this was conjectured by by Mickey and Nati. I tell you one ingredient of the proof. And this is, just, if f is a function to -1, 0, and 1 with small support. So suppose you have a function with small support, the support is t, and think about it as small, then most weight of the Fourier coefficient squared is concentrated above c log 1 over t. So it's concentrated for sets of large size. Well, not so large, but logarithmic in 1 over t. This is this sort of the crucial fact in the proof of this theorem. And this fact itself requires an inequality by Beckner, which since then had various other applications. Also, we discovered that Beckner was not the first. It was first discovered by Aline Bonamy a few years before Beckner. And in any case, this is something, if you want to know something about the proof, this is a fact which is not, it's not an immediate harmonic analysis fact, but it requires some proof. It's not terribly difficult. It requires a tool, and this tool, in the hypercontractive inequalities, turned out to be a useful tool for other purposes. Okay, here's the second theorem that I want to mention. And I want to mention is that this is theorem by Itai Benyamini, Oded Schramm, and myself. And it's about noise sensitivity. I should say, we wrote a paper about noise. Okay, I'll mention that. So the theorem said the following. Suppose that h of f is the sum of the... Okay, so you will not be able to understand what the theorem is from looking at these slides because there are some missing, crucial missing elements. One missing element, we are talking about monotone Boolean functions. So for a sequence of, here there is a little word monotone, which you cannot see from where you see. For a sequence of monotone Boolean function, we look at the quantity which is the sum of the square of the influences. And then it is not difficult to show that for monotone Boolean function, the sum of the squares of the influence is always at most 1. And if the sum of the square of the influences tends to 0, then the function is noise sensitive. And there is a simpler version of it which proved, I will not mention this version, I will just mention that a very strong, sharp, quantitative version of our result was just recently proved by Nathan Keller and Guy Kindler. I think it was completed a few weeks ago, and it's a very nice result. It's technically quite difficult. And this was the technique, and this is slightly counterintuitive because it says that if the influences are large, then if the influences are not large, then it's noise sensitive. So the only way that a function can be noise stable is if the sum of the squares of the influences is very close to 1. And this is a little counterintuitive, but it is nevertheless correct. And the reason, let me not, it's too late, but the reason we were interested in noise sensitivity is that we wanted to prove this consequence, the crossing event for critical planar percolation is noise sensitive. So if you want to base an election rule on percolation, so you divide the state into little counties, and in each county you see if Bush wins or if Gore wins, and if there is a top to bottom connected pass of Bush counties, then you give the victory to Bush, and if there is a left to right pass of Gore, then you give the... This is not a good election rule because it is noise sensitive. I mean, in case you wonder, had we found it is good, it would be hard to convince the public. So this is, well, this is a nice way to imagine what does it mean that percolation is noise sensitive, but I will not do it because we are running out of time. I'll mention there are other cases of noise sensitivity. One is related to a notion called first space equivalent, eigenvalues of random matters, but an important example where you have extreme sensitivity to noise is the the majority on 3's example by Ben or Lineal. So here and this is example, you have very strong noise sensitivity. Okay. Now let me mention, how much time do you have? 15 minutes. Okay. So let me mention a result. So I already mentioned to you that the influence of every variable for the majority function is square root n. 1 over square root n. And therefore the expected size of S for the Fourier coefficient is square root n. And I can tell you this is the maximum it can get for monotone function. So you think if the expected is so large, then majority should be very sensitive to noise. But this is not the case. Majority is stable to noise. Majority is stable to noise, and the reason is that most of the Fourier coefficients of majority are on small variables. It's true that the expectation is large, but most of the energy is on small coefficients, on sets of small coefficients. And this is equivalent to noise stability. And the fact that majority is noise stable and the precise statement was proved by Shepard, and it says, Nati was not worried, Noga was not worried that he already heard everything, but he wanted to know which jokes I'm going to repeat. And okay, you didn't see the joke yet, but Shepard's theorem says that suppose that there is a probability T for a mistake in counting each vote in the majority rule, then the probability that the outcome of the election are reversed is R cosinus of 1 minus T over pi. This is when the number of voters go to infinity. Yes, it's not precise for every n, but when n go to infinity, if you switch the outcome of the election, if you have majority and the voters votes at random and you switch the outcome of every voter with probability T, then the probability that the outcome of the election are reversed is R cosinus 1 minus T over pi. And this is from 1899. So it was, it's a long time ago. Even before I was born. And and this is, I just repeated the same theorem again. And when T is small, this behaves like a square root of T. Now, of course, the R function which are more stable to noise. And this is the dictatorship. And in a dictatorship, if the noise is T, the probability for flipping the outcome is T. But also weighted majority is and the question, you see, I'm ahead of my slides. Is there more stable voting rule? Sure, the dictatorship. But now I want to mention the third theorem I plan to mention, which is majority is stablest. And this is theorem of Mossel, O'Donnell, and Oleszkiewicz. Elchanan Mossel, Ryan O'Donnell. Now we talked about memory, but Oleszkiewicz. Krzysztof. No, the problem with Krzysztof is not so much to memorize his name, but to pronounce it. But in any case, I even didn't remember it. But Krzysztof, Oleszkiewicz, and they proved the following. They proved that majority asymptotically is the most noise stable method on the nose. And here is the statement. If Fn be a sequence of Boolean functions with diminishing maximum influence, so the maximum influence, Ik of Fn, there is an n missing here, n should be here. And then it's go to 0 when n go to infinity. Then it is 0. Then the probability the outcome of the election are reversed when every vote there is a probability is flipped is precisely this thing that Shepard proved. 1 minus little of 1, R cosinus 1 minus T over pi. So there's nothing better than majority. This is a very nice theorem, and it has some striking consequences. Okay, the first consequence is not so striking, but it says that the probability of cyclic outcome for voting rules with diminishing influences are minimized for the majority voting rule. So you know that you must know that it is possible that the majority of the society prefer candidate A to candidate B, and majority prefer B to C and C to A. And you can ask, if you have a voting rule, and what is the probability, and the preferences of the individual is random, what is the probability that such a catastrophe happened? And it turns out, of course, in the dictator it doesn't happen. But we are talking about, it turns out that if you insist that the power of each individual go to 0, then you cannot do better than majority. And this is a very nice result, but this was not the motivation of Elchanan, Ryan, and Khrushchev. Gzhistov. And the motivation was these things about the Gomans-Williamson algorithm. You know that there is a famous, the max-cut algorithm of Gomans and Williamson, which used semi-definite programming. They found an algorithm based on semi-definite programming for max-cut. I remember that it happened. It was quite striking. It was one of these days we are very happy in our profession, and 0.878567 precisely. I mean, not precisely, but it's some number. And I remember, the first instinct is let's try to do better. I don't know. You had this instinct. I just imitate this instinct. And many people tried, and it was a simple algorithm. You replace the graph by some vectors in Rn, and it looks that you can do better by something more clever, more complicated. We don't mind working a little bit to improve this. And then the result, and this relates to another result, it turns out that improving this will be computationally hard. Well, here we come to, it's not really NP hard, but it's hard, it's as hard as something which is called the unique gain conjecture. So there is a certain problem which is called a certain conjecture that unique gain in certain parameters is NP complete. And if it is true, then this is NP hard. In any case, I think this is a good evidence that this is hard. If you improve this even a little bit, then you will be able to improve the situation for a whole lot of problems, approximating problems. Part 3. Okay. Now there are two conjectures, but as I already told you, I will describe briefly one conjecture. In fact, one conjecture with two variations. The first conjecture is the following. Suppose you have a monotone, I should say, what is monotone threshold circuits? So I assume that you all know what are Boolean circuits. But let me tell you what they are, and if I don't know, you can correct me. You have inputs, then you have gates in several layers. Each gate takes a bunch of the gates in one lower layer, and either take their OR or take their AND. And let's say that in the first layer you allow either a variable or its negation, and then there are several rounds like this, maybe many rounds, and at the end you have the outcome. So this is a very basic model in computational complexity. If you can prove that there's no polynomial circuit which compute if graphs have a Hamiltonian cycle, you will prove that NP is not P with a little changing, because it is stronger statement. But what we can deal with are usually circuits of bounded depths. They are already extremely interesting and quite intriguing. But now we make the circuit, the gates, more powerful. Every gate can be a weighted majority gate. This is called a threshold circuit. Now, if we allow the weights to be only positive, then this is called a positive or a monotone threshold circuit. If we allow also negative weights, then this is a general threshold circuit. The computational power of general threshold circuits, even of bounded depths, is a big mystery. It's already well beyond the horizon of a complexity theory of lower bound. Here are two conjectures. The first conjecture says, if you have a monotone Boolean function described by monotone threshold circuits of size m and depth d, then f is stable to noise, well, not to a constant, to noise which is of size 1 over log m to the power 100d. Yes? Ah, 5 minutes. Oh, okay. I thought you had 5 questions. 5 questions. Let's have them one at a time. Okay, it's a good time to have 5 minutes. And you see, I used here the word monotone twice, and it's really redundant because if the threshold circuit is monotone, then the outcome is automatically monotone. But then the second and even more daring conjecture says the same is true for monotone functions described by arbitrary threshold circuits. So if you have a monotone function which is described by arbitrary threshold circuit, then it is also noise stable. And let me mention some things about these conjectures and where they come from, how they relate to other things we know. I think conjecture 1 is sort of realistic. I mean, it will have some consequences which are not known. It will reprove some things we know. Since it deals with monotone threshold circuits, it is not something which is out of reach or we believe is out of reach. You can hope to do something by induction. We did try induction on the depths. We did try with various people. We didn't get much. But I think it's not entirely a hopeless conjecture. The second conjecture is sort of intriguing. It's fairly reckless. And let me tell you what are the consequences of this conjecture. So let's take the majority of Swiss. I already mentioned this function, the majority of Swiss. Maybe you remember the 3 counties, 3 cities, 3 neighborhoods, 3 streets. So, and this function is extremely noise sensitive. And the first consequence, conjecture 1 implies that this function is not in monotone TC0. It cannot be expressed by monotone threshold functions of bounded depth and polynomial size. And you know, this may already be known by results by Andy Yao and Hastad and Goldman. I'm not entirely sure, but something very close to that is known. The second conjecture is that it cannot even be, this function cannot even be approximated. So it agreed on most inputs on a function in monotone TC0. And this is already beyond the knowledge. We don't have any example of a function that cannot be approximated by monotone functions in TC0. And this, I would say, I don't know, semi-realistic goals. The consequence, the third consequence, is that this recursive majority of 3 is not even in TC0. Now, this is generally believed to be true. And the fourth conjecture is it cannot be even approximated by function in TC0. I would say that the fourth conjecture, I'm not sure it's true at all. But, you know, I would bet that I hope it's true. The third consequence is believed to be true, but it's believed to be, it's almost outside the boundary of the known method because of something very interesting which is called the natural proof barrier. There is some obstacle to proving result, which is, I'm not telling you what it is. First of all, you know probably better than me, and second of all, this is not the time to start what natural. But the point is that this does not, the natural proof results, and there are some relevant results about threshold function by Moni Naor and Omer Reingold. They don't really fail this conjecture. So you can regard conjectures, the conjecture 2 and consequence 3 as a way to go around the natural proof barrier. And you know, probably it will not go around the barrier because it's probably easier to extend the barrier, or you know, also it can be simply false regardless of the barrier of the natural proof. But as far as I know, it doesn't fail automatically because of the natural proof So it's quite interesting to see, also to look at Omer and Moni examples to see what do they tell us about constructions of such function. I think it's fairly interesting. It may be that even the first conjecture is false. In any case, I think these conjectures are interesting. And just I want to conclude. Yeah, so I discuss it on my blog. I have a blog. You can look there. Probably you can find there more interesting things than this, but you can find this. So there's three things. I already mentioned the third. AC0 analog, I should mention in one word. For AC0, everything that I conjecture is known to be true, not only for the notion of noise sensitivity, but for the stronger notion of influences. So if you translate things from noise sensitivity to influences, you get results, non-result by Hastad, Bopana, Lineal, Mansour, and Nissan, and others, which tell you that the Fourier description, the influences behave well for function in AC0. The other thing which is very intriguing is, you see, I said I have a conjecture about monotone function which can be described by monotone circuits, and I have a reckless conjecture about monotone functions that can be described by arbitrary circuits. But the question is, can you show me a single monotone function that cannot be described by, can you show me a single monotone function in AC0 or in TC0 that cannot be described or approximated by a monotone circuit? A monotone circuit in AC0 and TC0. So I told you 4 problems, and for one of these problems, there is a result by Yuri Gurevich and Miki Aitai, which show that there are functions which are monotone, they are in AC0, but they cannot be precisely described by a monotone AC0 circuit. It's a fairly difficult paper. As far as approximation, there's no such result, and as far as TC0, there's no such result. So the fact that I said that the 2 conjectures, one of them is plausible and one of them is reckless, the problem to find any function which shows that these conjectures are not identical is also open. So I think I'll end here. Thank you very much.